We're looking at an explosion, and remember, in an explosion we conserve momentum, so there is conservation of momentum in this, and we're going to notice the kinetic energy of this system will also go up greatly when the explosion happens. The momentum before for this system, so the momentum before should be equal to the momentum after. Let's draw a picture of what's going on in this problem because I think that makes it a lot easier to kind of look at. We've got one object that goes in the positive y direction, and that object has a mass equal to 2 kilograms. We also know that its speed is approximately 200 meters per second. So the momentum for the first object, let's just call this the first object, is 400 kilograms times a meter per second. We have another object then that goes to the east, which is right. We'll call that the x direction. And we see that this one, the momentum should be equal to its mass, which is 4 kilograms times 100 meters per second. So it's also 400 kilograms times a meter per second. Just by observing this, you'll notice that this third projectile, so projectile 3, which has a mass equal to 3 kilograms, will have a speed in both directions, in both the x and the y, but it'll be going in a negative y and a negative x in order for that to be conserved. So to do this, we know that because the momentum before is equal to the momentum after, the momentum before is equal to 0, and the momentum after is going to be equal to momentum 1 plus momentum 2 plus momentum 3. The problem is I can't just plug them into this equation because they're going in different directions. So I need to look at this for both the x and the y direction. Let's do the sum of the momentum in the x direction. We know that should be equal to 0, and that would be equal to, notice P1 is only in the up and down direction in the y direction, so there is no momentum for that object in that direction. Plus the momentum of the second piece is 400. And then we're unsure of what the momentum in the x direction is for projectile number 3. If I go through and solve for P3, I find out that P3 in the x direction should be equal to negative 400 kilogram meters per second. Let's go ahead and do the same thing in the y direction. The sum of the momentum in the y direction should be equal to 0, and that's going to be equal to 400 for the first projectile, 0 for the second one. We're not sure what the third one is, and once again we get for the third object in the y direction, the momentum is also negative 400 kilogram meters per second. If I want to, I can either solve for the entire momentum of this object and then finally for the speed. So let's go ahead and let's solve for the final momentum of the object. To do that, I've got an x and a y, so I know that the final momentum of object number 3 should be equal to the square root of the first momentum squared plus the y momentum for that object squared. And when I'm done, I find out that the momentum of this object in the end is 565 kilogram meters per second. So this is kilograms times a meter per second. If that's the momentum, I know that momentum is equal to the mass, which is 3, times the velocity change. And so if I take 565 and I divide it by 3, I end up with 188 meters per second. So that would be the magnitude, would be 188 meters per second, but I still need to know the direction. Specifically what I'm trying to do is I want to know what is the angle that I make with the horizontal. To do that, I can just say that the angle would be equal to the inverse tangent of the y, and notice that our y momentum is 400, our x momentum is also 400, so I've got 400 divided by 400, which is 1, and the inverse tangent of 1 is 45 degrees, and so that would be my direction. 565 is the momentum. We know that the velocity is 188 meters per second at 45 degrees south of west. And that is the end of that more complicated problem.